Hello students. So, we will continue our discussion of derivatives. So, in the previous lectures we have learned some of the properties of derivatives like the product rule, quotient rule, etc. And in this lecture we will learn a very important rule which is called the chain rule of derivative. So, let us start with the chain rule. So first of all, let us recall what is composition of two functions. So we denote suppose f and g are two functions, then we denote by f compose g. This is defined as f of g of x, right. So if we have two functions f and g, and the range of g is contained in the domain of f, then the composition is defined and it is nothing but f of g of x. So what we would like to know is, suppose we know g is differentiable at some x equal to a. So let me write g of x is differentiable at x equal to a, and the function f of x is differentiable at x equal to g of a, then is the composition f compose g of x differentiable at x equal to a, and if so, then can we write the formula for f compose g prime at a. This is what. So let us try to see. So let h of x is the composite function, this is f of g of x. Then to check the derivative, so to check whether h of x is differentiable at x equal to a, we need to look at the limit h going to 0 of let me write this composite function as k of x. So k of x plus a plus h minus k of a divided by h, that is same thing as limit of h going to 0, k is f of g of a plus h minus k of a is f of g of a divided by h. Now, if g of a plus h minus g of a is non-zero in some open interval containing sorry. So, let me write like this. So, if g of a plus h minus g of a is non-zero, for all small h is non-zero, then we can write f of g a plus h minus f of g of a by h. This can be written as f of g a plus h minus f of g of a divided by g of a plus h minus g of a and times g of a plus h minus g of a divided by h. So, this we can do if this g of a plus h minus g of a is non-zero. Now, what we know is that we are given that g is differentiable at a. So, the limit of h going to 0 of g of a plus h minus g of a by h, this exists and this is the derivative g prime of a. So, this is the second factor here in the product. Also, f is differentiable at g of a. So, limit of h going to 0 of f of g of a plus h minus f of g of a by g of a plus h minus g of a this is equal to the derivative of f at g of a. This is because as h goes to 0, g of a plus h minus g of a plus h goes to g of a. This is since g is continuous at a. We have seen that if g is differentiable at a, then it is also continuous. So, this denominator goes to 0 and then this limit is same as writing as f of say y minus f of g of a divided by y minus g of a, and I can write this y going to g of a, and this we know is equal to f prime of g of a. So, we have got this formula. So, if g of a plus h is not equal to g of a for small h, then f prime then f compose g prime at a, this is equal to f prime of g of a times g prime of a. So, the chain rule says that this is true even if we do not impose this condition. So, in fact, the above formula is always true. So, let me write this theorem, chain rule. So, let f and g be two functions such that f is differentiable at g of a and g is differentiable at a, then f compose g is differentiable at a and the derivative is given by f compose g prime of a is equal to f prime of g of a times g prime of a. So, let us first see the proof of this. So, we need to show that limit of f of g of a plus h minus f of g of a by h, this is equal to f prime g of a times g prime of a. So, what we will do is because we do not know whether we can divide by g of a plus h minus g of a. So, we define a new function phi of y, this is equal to f of y minus f of g of a divided by y minus g of a. This makes sense only if y is not equal to g of a, and if y is equal to g of a, we can define this as f prime of g of a. We know that f prime of g of a exists. So, phi of y is a function defined in this form. If y is not equal to g of a, this is f of y minus f of g of a by y minus a, and it is equal to f prime of g of a if y equal to g of a. Now, one important thing is that this function then becomes continuous. So, if we look at limit of y going to g of a of phi of y, this is equal to limit of y going to g of a of f of y minus f of g of a by y minus g of a. Now, because it is given that f is differentiable at g of a, this difference quotient, this goes to f prime of g of a. This is since f is differentiable at g of a. But by our definition of phi, f prime of g of a is nothing but phi of g of a. So, the limit of phi of y as y approaches g of a is same as phi of g of a, and this implies by definition of continuity that phi is continuous at g of a. So, this is one important fact. Now, note that f of y minus f of g of a, this is equal to phi of y times y minus g of a. This is true for all y. So, if y is not equal to g of a, then we know that phi of y is equal to f of y minus f of g of a divided by y minus g of a, and therefore, by multiplying by y minus g of a, f of y minus f of g of a is equal to phi of y times y minus g of a. So, of course, this is true if y is not equal to g of a, but if y is equal to g of a, then you notice that left hand side is f of g of a minus f of g of a, which is 0, and right hand side if you put y equal to g of a is again 0. So, the above equality is true even if y is equal to g of a. So, now to find the limit of f of g of x minus f of g of a, we just put, so put y is equal to g of a plus h, then what do we get? F of g of a plus h minus f of g of a is equal to phi of g of a plus h times g of a plus h minus g of a. So, therefore, if h is non-zero, we can divide, write f of g a plus h minus f of g of a divided by h. This is equal to phi of g a plus h times g of a plus h minus g of a divided by h. Now, in the right hand side, so in RHS, limit of h going to 0 of g of a plus h minus g of a by h. This we know is equal to g prime a, because g is differentiable at a. And what about the other limit? We get limit h going to 0 of phi of g a plus h. But what we have seen is that phi is continuous at g of a. So, this is equal to phi of g of a, since phi is continuous at g of a. But what is phi of g of a? By definition of the function phi, this is equal to f prime of g of a. So, therefore, limit of h going to 0 of f compose g of a plus h minus f compose g of a divided by h is equal to f prime g of a times g prime of a. That is, f compose g prime of a is equal to f prime g of a times g prime a. So, this proves the chain rule. So, one comment so, if you see when we wrote this difference quotient as f of g of a plus h minus f of g of a by g of a plus h minus g of a, here we have to assume that this g of a plus h is not equal to g of a for small enough h. So, if you see it, this might happen. So, remark g of a plus h minus g of a is not equal to 0, might not hold true for small enough h, no matter how small h you choose. So, as an example, consider the function g of x is equal to x square sine 1 by x. So, this function, first check that for this function g is differentiable at 0. So, let us check that claim. G is differentiable at 0 and g prime 0 is equal to 0. So, let us calculate. So, limit of h going to 0 of g of 0 plus h minus g of 0 by h, this is equal to limit h going to 0, g of h is h square sine 1 by h, or let me write this is defined for x not equal to 0 and 0 if x is equal to 0. So, g of x I have to define at 0 also, and then this function we claim is differentiable at 0. So, this is h square sine 1 by h minus g of 0 is 0 divided by h. This is same thing as limit h going to 0 of h times sine 1 by h. Now, we have dealt with limits of this form. So, this is equal to 0, this is because we know that sine 1 by h is always less than equal to 1. So, this implies that mod h sine 1 by h this is less than equal to mod h, and of course, this is greater than equal to 0, and then by sandwich theorem limit of h sine 1 by h is equal to 0. So, this function x square sine 1 by x for x not equal to 0 and 0 at x equal to 0, this function is differentiable at 0 and the derivative is equal to 0. But if you see for this function, but g of, if I take any 1 by m pi, this is equal to 0 for all integers m. This is because sine of m pi is 0 for all m in integers. So, g of 1 by m pi, if you do, it will be equal to 1 by m pi square times sine of m pi, which is 0. And notice that if you take any interval around 0, so no matter what interval you take, there exists for large enough m 1 by m pi will be in this. So, for any delta greater than 0, 1 by m pi, this belongs to minus delta delta for some m in integers. So, this is because I mean you might think that to prove this, it is enough to do this for when g of a plus h is not equal to g of a, and think that if the function is not constant, g is not constant, then it must happen that in a small enough interval g of a plus h is not equal to g of a, but that is not true. This example shows that. Now, let us write this chain rule in some other forms. So, if we write y is equal to let me write y equal to g of x and u is equal to f of y. Right. So, this is writing the composite function. So, that is u is nothing but f of g of x, which is f compose g of x. Right. So, any composite function composition can be written like this. You define y to be equal to g of x, the inner function, and then u is equal to f of y. So, then the chain rule says that if g is differentiable at x and f is differentiable at g of x, then f compose g prime at x is equal to f prime of g of x times g prime of x. So, what is g prime of x? So, that is we can write f compose g is nothing but the function u. So, this is same thing as du by dx is equal to f and g of x is y. So, this is f prime y, which is d u by dy times dy by dx. Right. We have y equal to g of x. This implies that dy dx is g prime of x and u is f of y. So, du dy is nothing but f prime at y, which is same as f prime of g of x. So, we can remember the chain rule as if I have u is equal to f of y and y is g of x, then to find the derivative du dx, you first find the derivative of u with respect to y and then multiply it by derivative of y with respect to x. So, this is easy to remember, because if you see, if this was usual division, then this dy cancels and then we get du dx. So, that is the way you can remember it, but note that du dy, this is just the symbol for the derivative, it is not the quotient of two things. So, now let us see some examples. Let f of x is equal to say x square plus 1 cubed, and then find f prime x. Right. So, what are the ways you can do? So, one way is that you can expand x square plus 1 cube, this will be equal to x to the 6 plus 3 times x to the 4 plus 3 x square plus 1, and therefore, now we know the derivative of x to the n. Therefore, f prime x is equal to 6 x to the 5 plus 12 x cube plus 6 x. So, this is one way. Another way is you could use product rule. So, if I want to find the derivative, we write x square plus 1 times x square plus 1 square, and then this is our f of x. So, f prime x is the derivative of the first function 2x times x square plus 1 square plus x square plus 1 times the derivative of x square plus 1 square, and for this you again use product rule. So, this is 2x times x square plus 1 plus x square plus 1 times 2x, which is equal to 4x times x square plus 1, and therefore, f prime x is 2x x square plus 1 square plus 4x times x square plus 1 square. This is 6x times x square plus 1 square, and you can see that this is same as the previous answer. This is same as 6x times x to the 4 plus 2x square plus 1, and if you multiply we get 6x to the 5 plus 12x cube plus 6x. So, we get the same answer, but there is another way to do it using chain rule. So, using chain rule, so we have f of x is x square plus 1 cubed. So, this is equal to g of x cube, where g of x is x square plus 1, right. So, now f of x is g of x cube, where g of x is x square plus 1. By chain rule, the derivative is f prime x is equal to the derivative of cube will give me 3 times g of x square times g prime of x. This is equal to 3 times g of x is x square plus 1 square times g prime x gives me 2x. So, this is equal to 6x times x square plus 1 square, which is the same answer that we got using the product rule. Or you can write y is equal to x square plus 1 cube. This you write as u cubed, where u is x square plus 1, and then we know that dy dx, y is a function of u now. So, we write dy du times u is a function of x. So, du by dx, and dy du is the derivative of u cubed gives me 3 u square times du dx gives 2x, and then you have to write everything in terms of x. So, this is 3 times x square plus 1 square times 2x. Right. So, using chain rule, it makes the calculation easier, and we will see some more examples. So, find the derivative of the sine of x square. So, here if you see, we cannot even use product rule or do any simplification to find the derivative. So, either you have to find using the limit, or if you notice that you can use chain rule here. So, we write this. So, write y is equal to sine of u and u is equal to x square. So, dy du will give cos u and du dx is 2x. So, the derivative dy dx, this by chain rule is dy du times du dx, which is equal to cos of u, which is x square times 2x, right. So, what this chain rule does is that you have sine of something, you know the derivative of sine is cosine. So, you find the derivative of the outer function first and then evaluate it at this inner function, and then you find the derivative of the inner function. So, after some practice you will be able to write this directly. Let us make it more complicated, and suppose I want to find d by dx of sine square of say x cubed. So, here if you notice sine square x cube, this can be written as composition of three functions. So, sine square x cube, this is equal to sine of x cube and then you square this, right. So, here the outermost function is you square this and then you have sine of x cube. So, the derivative so this is my function y. So, dy dx, first you have this u squared, the derivative of that will give me 2 times sine of x cubed, and then we have to write derivative of sine x cubed. Now, like the previous example, this derivative sine x cube is nothing but first you take the derivative of sine, you get cosine of x cube, and then derivative of x cube will give 3x square. So, this gives me the derivative. Let me do maybe one more example. So, I can make it some sine of cosine of x So, if you have to find the derivative dy dx, here the outermost function is sine of something. So, you get cosine of this whole thing, then you have to take the derivative of sine of this. So, times, okay, let me write once more, dy dx of sine of cosine x cube plus x. Then you again use chain rule. So, this will give me cosine of cosine x cube plus x, and then the derivative of cosine x cube plus x, again you use chain rule for that. So, that gives me negative sine x cube plus x, and then multiplied by derivative of the innermost function x cube plus x will give 3x square plus 1, right. So, using chain rule we see that we can easily find the derivative. If we have composition of more than 2 functions, then you use chain rule repeatedly to find the derivative of the composition. Now, next thing we will like to see if we can find derivatives of inverse functions. So, for example, you would have studied about inverse trigonometric functions. So, we would like to ask what is d by dx of sine inverse x, d by dx of cosine inverse x, tan inverse x, and so on. So, suppose let y equal to f of x, and suppose this function suppose f of x has an inverse let me write g of x. So, what does that mean? That is f of g of x is equal to g of f of x and it is equal to x, right. So, the inverse means that if you take f of f inverse of x, you get x, and f inverse of f of x is x. So, if we have y equal to f of x, then x can be written as f inverse of y, which is same as here g of y. So, now to find the derivative, so if we look at, so therefore, g prime of y, this is nothing but dx dy right, and what we know is that since f of g of x, this is equal to x, which is this implies g of x we are writing so we have, if I take the derivative of this, then with respect to x I get 1 is equal to d by dx of f of g of x, and this by chain rule is equal to f prime g of x times g prime of x. What we would want is to find the derivative g prime x. So, if f prime of g of x is not equal to 0, then g prime of x is 1 by f prime g of x. Right. So, what we get is that so the derivative of if f inverse denotes the inverse of f, then d by dx of f inverse of x, this is equal to 1 by the derivative f prime at f inverse of x. So, what we need is that f prime at f inverse x should be non-zero. So, for example, let us try to calculate the derivative d by dx of sine inverse of x. So, by this formula, this is equal to 1 by the derivative of sine. So, let me write 1 by f prime of sine inverse x, where f x is equal to sine of x. So, the derivative of sine of x gives cosine. So, this will be cosine of sine inverse x. And what is cosine of sine inverse x? So, if y is equal to sine inverse x, this means that x is same as sine of y, and we want to find what is cosine of y. So, this implies cosine of y, cosine square y is equal to 1 minus sine square y, which is 1 minus x square. So, cosine of y is equal to plus or minus square root of 1 minus x square. Now, what do we know about sine inverse x? This is defined for x between minus 1 and 1, right, because sine of x range is between minus 1 and 1. So, sine inverse x is defined for x in minus 1 1, and this sine inverse x this belongs to 0 to pi by 2 if x is in 0 to 1, and sine inverse x is in minus pi by 2 to 0 if x belongs to minus 1 to 0. So, if x is positive, then sine inverse x is in the first quadrant between 0 and pi by 2, and if x is negative, then sine inverse x is in minus pi by 2 to minus pi by 2 to 0. Now, what about cos of this? But cos of theta is positive if theta is between minus pi by 2 to 0, minus pi by 2 to pi by 2. Right. In the first quadrant and fourth quadrant, both cosine is an even function. So, it is always positive in minus pi by 2 to pi by 2. So, therefore, cos of sine inverse of x, this is positive for all x between minus 1 and 1. So, this cos of sine inverse x we wrote here cos of sine inverse x is plus or minus square root of 1 minus x square, but we know that it has to be always non-negative. So, cos of sine inverse x is equal to square root of 1 minus x square. This is true for all x, and it is true for in the closed interval minus 1 1, but then so therefore, the derivative d by dx of sine inverse x, this is equal to 1 by square root of 1 minus x square. So, I will do one more, the derivative of tan inverse x. So, if we write y equal to tan of x, so tan inverse x, and we want to find dy dx. So, sometimes it is easier to write this is same thing as writing x equal to tan of y, and therefore, if I write dx dy, this is equal to derivative of tan y gives me secant square y. So, therefore, dy dx, note that by chain rule or by chain rule, this is equal to 1 by dx dy, and this is equal to 1 by secant square of y. Secant square y is same as 1 plus tan square y, and tan y is equal to x. So, this is 1 by 1 plus x square. So, therefore, the derivative of tan inverse x is equal to 1 by 1 plus x square. Right. You should try to calculate now the derivative of other inverse trigonometric functions, and then in the next class I will write down the formulas for those, and then we will also find derivatives of some other functions. Thank you.